Hello, this is my demonstration on my final project titled An Adaptive Octree-Based Isosurface Extraction System for Visualizing Antenna Radiation Patterns. This project addresses a fundamental problem in scientific visualization. How do we effectively extract and render complex 3D surface from volumetric field data while maintaining both visual quality and real-time performance? What makes this interesting is that traditional uniform grid approaches waste enormous computation resources processing empty space. My adaptive Octree implementation intelligently focuses computation only where the data is complex, achieving up to 75% reduction in triangle count for simpler regions while maintaining full detail where needed. Let me show you the problem we're solving. Here in the GUI, I can select the scenario that I want to visualize. We have different scenarios in Uyun PPM visualizer. There is ideal localizer, ideal glide slope with Boeing 777, ideal localizer with hangar, and other scenarios. After I select the scenarios, I can select the field type from the field drop down here. I can use CSBCRS, SBOCRS, CSBCLR, or SBOCLR. And here's the button that we can use to load the dat file for the visualization. Let me browse the dat file. Since I'm using the localizer, I need I would like to select the ideal localizer.dat file, and after loading the dat file, we can see the loaded dat file's name in here. This data represents field distance values through a 3D volume, in this case a 31 by 31 by 31 grid covering the radiation pattern around an antenna. And I need to init the scenario and generate output and then pass the output. And I can use generate single isosurface button to extract isosurface using standard marching cube. This processes every single cell in the grid uniformly. For our relatively small grid of about 30,000 cells, clicking this generates 2500 triangles and around takes around 30 milliseconds to generate the isosurface. But here's the key insight: most of this volume is empty space or contains very uniform data that doesn't need fine detail. Now let me come to my solution. My solution uses three key technical components working together. First, I need to generate sign distance field using generate STF button here. Before I before I can generate STF, I can change the STF ISO values or max from here, and it generates SDF by subtracting the ISO value from the magnitude in the parsed output file from the parsed output file from we did earlier. It ex- it subtracts the ISO value and builds a sign distance field. Once the sign distance field is generated, I can use build Octree button here to build an adaptive Octree. I can before I build the, the Octree, I can increase or decrease the maximum depth of the Octree from here. This bud here. Let me demonstrate by setting max depth to 6 and variation threshold to 1 e to the power negative 4. Now if I click on the build Octree button, and we can see the statistics here. The statistics show that there are a total of 1,85,761 nodes, out of which 1,62,541 are the leaf nodes and 41,155 leaf nodes contains the ISO value. The spatial is the architecture works through recursive subdivision, starting with a single cube encompassing the entire volume. The examines each region and asks, does this region have high field variation or does it contain the isosurface? If yes to either of the question, it splits into 8 child cubes and repeats the process up to the maximum depth of 6. This, this is implemented in my build adaptive Octree class in the code, which maintains the tree structure and provides methods for querying which leaf nodes contain the surface. The key innovation is their dual criteria splitting, combining both field variation analysis and isosurface proximity. Once we have the Octree built, we extract the actual isosurface using the marching cubes, but instead of running marching cubes on uniform grid, we run it only on the Octree leaf nodes that contains the isosurface. To extract isosurface from STF, we can use the extract isosurface from STF button here, and we can see the isosurface here. Let me hide the isosurface generated using standard marching cubes. My Octree marching cubes class in the code handles the isosurface extraction from Octree marching cubes. The extraction processes those 40,155 ISO leaves and generates the result. I can see the performance metrics in the terminal. You can see that out of 30,155 processed leaves, the marching cubes generated 68,479 triangles and 1,36,323 vertices, and it goes up to average depth of 5.96 to generate the surface. And we can see from the console log that the adaptive Octree method produces 2,639 percentage more triangles than standard marching cubes, given that the Octree level is 6. The performance matrix tells an interesting story for our small 31 cube grid with a complex antenna pattern at max depth 6 and variation threshold of 1 e to the power negative 4. The adaptive method subdivides heavily everywhere, producing more triangles than needed. But what happens if I decrease the max depth for Octree? If I click build Octree, extract isosurface from STF, we can see that STF is isosurface is getting changed and the number of triangles being updated. If I click build Octree and extract isosurface for the depth maximum depth level 4, we can see that the total nodes processed is 4,331 and number of triangles is 3,355 and vertices is 6,705. As the number of depth decreases, the triangle numbers and vertices also decrease. But if we increase the maximum octave depth, the number of triangles and vertices also increases. I also have implemented a multi-resolution extraction method. If I check the multi-resolution extraction method button, you can select the depth for which I want to generate the isosurface. Let me select the minimum depth at 2 and maximum depth at 4 and build Octree, extract isosurface. We can see that isosurface is updating accordingly. It collects the leaves from the specified minimum depth to maximum depth and merges them into a single isosurface. I also have implemented the view dependent level of detail. If I go away from the camera, the isosurface will change. Let me go far away. It updates every 50 meter as I go away towards the camera. It adds more detail. It uses all level of octave depth to update the view dependent level of detail. And I can also change the color of the isosurface from here. I have hue start. If I change the hue, we can see in the light that the color of isosurface is being changed. The color is everywhere same because I have used the isosurface magnitude to color the isosurface. Since each isosurface, every point on the isosurface has the same magnitude, the color it gives the same color everywhere. And I have also some preset buttons like red to blue and blue to red, green to red, or I can use the full spectrum are the preset buttons to change the color, or we can use manually from here. Let me clear this isosurface and try with another method. Let me select ideal glide slope, select the ideal glide slope, the data init, generate output, pulse output, then generate single isosurface. We can see the ideal glide slopes isosurface at 1 e to the power negative 5 iso value. And if I generate SDF, field Octree and extract isosurface, you can see the isosurface in here. It looks slightly different than the actual traditional marching cubes. Let me hide it. Sorry, I got an error. Maybe there is something wrong. Let me do it again. Let me need the ideal glide slope. Browse for the glide slope the data. Init, generate output, pass output, analyze the surface, and generate SDF, build Octree, extract isosurface. This is what the isosurface looks like from different view. Let me try one more another data type. Let me try with WI 1410 antenna. Generate output and pass output. We can see the isosurface. Now let me build HDF, Octree and extract isosurface. At level depth level 2, the isosurface looks like that. If I increase the level, we can see the isosurface is changing. To summarize, I have built an adaptive Octree-based isosurface extraction system that intelligently balances detail and performance for electromagnetic field visualization. The system achieves significant geometry reduction when properly tuned. We saw up to 75 fewer triangles at lower depth, and while maintaining visual fidelity where it matters. The implementation demonstrates mastery of several advanced topics: spatial data structures with octaves, field-based STF generation, adaptive level of detail system, and real-time performance optimization. The GUIP provides comprehensive control through these parameter sliders, checkboxes, and buttons with immediate visual and numerical feedback. Future enhancements Future enhancement could include a GPU accelerated octet reconstruction, temporal coherence for animation fields, and automatic parameter selection based on data characteristics. But even in its current form, this system provides a powerful tool for interactive exploration of complex antenna patterns. Thank you for watching.